Section 1.3, graphs of functions. Does each graph represent a function? So go back and review our definition of a function. Remember, a function says that every input or domain value has to have exactly one output or range value. We can use what is called a vertical line test when we have the graph of a function to determine whether or not it is a function. What this vertical line is representing is every single different value of x. So right now this vertical line is representing x equals -4, x equals -3, x equals -2. And what we're doing as we pass this vertical line over this graph is we are looking to see, are there any spots where this graph touches the vertical line more than once? And you can see pretty clearly that there is not. And again, what that would represent, if it was touching twice, let's say here at 1, if it was touching up here and down here somewhere, that would mean that there are two x values that are giving us two outputs, which we know cannot happen if it is a function. In this case, since there is no spot where it touches more than once, we know that this is a function. Does this graph represent a function? Well, when I start taking this vertical line, what happens as soon as I get inside the circle? Oh, touching twice right here and right here for this x value. So this is not a function. So when you have the graph of a relation, use a vertical line test, pass an imaginary vertical line over the graph. If it is ever touching the graph in more than one spot, you know that you are not working with a function. Find the domain and range of the function. F of x equals the square root of x plus 1. Let's start with domain. We can find that algebraically pretty easily. In this case, we have an even index radical. So I know we have a possible domain restriction because the stuff underneath the radical can only be greater than or equal to 0. Solve that. X has to be greater than or equal to -1. So there's our domain. From -1 out to infinity. To identify the range, we're going to go to our calculator and put that function in. Oops. Let's go to our calculator and put in y equals the square root of 1. Square root of x plus 1. Graph. You can see a couple things here. From our graph, we can see our domain. How far left does the graph go? It goes to -1. How far right does the graph go? To infinity. So there's another way graphically we could get the domain. Range, you're asking yourself the question, how far down does this graph go? Well, it only goes down to x equals 0. Eventually, how high is the graph going to go? Up to infinity. So our range is from 0 to infinity. So when you're identifying domain, I want you to show algebraically how you get the domain. You can verify that from the graph, and you can get the range also from the graph. Next group of problems. Determine the intervals for which each function is increasing, decreasing, or constant. When we're talking about increasing, decreasing, or constant intervals of a function, okay, those will always be open intervals. So you will never, ever have a bracket when you are talking about a function increasing, decreasing, or staying constant. They will always be open intervals, so you'll be using parentheses every single time. Now, this will be a problem on the test that'll be missed a lot, and it should be really easy points if you can remember a couple things. Okay, the only time you are going to use y values ever in interval notation is when you are describing range. You will never, ever, ever use y values to describe any other type of interval other than range, and that's going to be the most missed thing on this problem on the test. So we want to know, when is the function increasing? When is the function decreasing? And when is the function staying constant? To do that, imagine that you are riding along this curve from left to right. As we travel along this curve from left to right, what are we doing in this interval right here? We are increasing. We're increasing from what x value? Well, how far left does that increasing interval go? Starts at x equals negative infinity and goes up to x equals negative 2.3. As we continue traveling along this curve, and now I'm going from this point down here, now we are no longer increasing, we are decreasing from x equals negative 2.3 to x equals positive 2.3. Once we get to that point, what are we doing over the rest of the function? Now again, we are increasing from where to where? From x equals positive 2.3 out to infinity, and this function never is staying constant. Again, a couple things to remember. Always open intervals. Notice everything's a parenthesis. Second thing is always use x values to describe increasing, decreasing, or constant, or you can just think of the only time I'm going to talk about y values is if I'm talking about range. Okay, second one here, as I start on the left and I begin traveling along here, from there to there, our function is increasing from negative infinity up to negative 1. In this middle section from here to here, our function is staying constant from negative 1 to positive 1. And in the last section here, our function is decreasing from x equals 1 out to positive infinity. Approximate the relative maximum or minimum for each function. You see the words approximate, that is telling you go ahead and use the calculator. So let's go ahead and put this function into the calculator. Y equals negative 3x squared minus 2x plus 1. We can see that that function has a maximum value up at the top here. If we go into our calculate menu, what are we trying to calculate? We're trying to calculate a maximum. So select number 4. It's going to give you the same set of directions that it gives you when you are finding a 0. Set the left bound. So go to the left of where that maximum point occurs, hit enter. Go to the right of where that maximum point occurs, hit enter. We don't need to guess, so hit enter again. And there is our maximum. You should recognize those two decimals and be able to give a fraction answer here. That is going to be a maximum value, so make sure you identify it as a maximum or minimum. It's a maximum at the ordered pair, negative 1/3, 4/3. Letter B, y equals 3x squared minus 4x minus 2. Put that function into your calculator. Try that again. 3x squared minus 4x minus 2. we can see that this function is going to have a minimum value down here at the bottom. So go back into your calculate menu. This time we are finding a minimum. Do the same thing, set your left bound, set your right bound, hit enter again. You should recognize this decimal as well as being 2/3 negative 3 1/3. So go ahead and record that as a minimum at 2/3, comma, negative 3 1/3 or negative 10/3. Okay, getting back to graphing piecewise functions, so let's take a look at both of these. Y equals x plus 1 for x values less than or equal to 2. Y equals 1 minus x for x values greater than 2. Let's start with the top piece. I'm only graphing that for x values less than or equal to 2. Take that domain value right on the edge, in this case 2, plug that in first. When x is 2, we get out 3, and that is included here, so that's going to be a filled in dot. Now I'm graphing this line only to the left of that point. So our slope is 1. So for this line, I can go down 1 and to the left 1. Down 1 and to the left 1, and so on. There's our first piece. Second piece, we are graphing only for x values greater than 2. So again, go to that edge value of 2, plug it in. We get 1 minus 2, which is negative 1. So for this piece of the graph, when x is 2, y is negative 1, that's down here. It's not included there because it's just x values greater than 2. So that's going to be an open dot. And now we can use this slope of negative 1, go down 1 to the right 1, down 1 to the right 1, and so on. And there's our second piece. Letter B. First piece, we're graphing for x values less than or equal to 1. So again, go to that edge domain value of 1. Plug 1 in. We get out 5. So order pair 1, 5. It is included there, so that's going to be a filled in dot. Now we can use our slope of 2 to graph the rest of this. Go down 2 to the left 1. Down 2 to the left 1, and so on. There's our first piece. Second piece, x greater than 1. Plug in that edge domain value of 1. We get negative 1 plus 4 is 3. So at 1, we're up here at 3, but it's not included in this piece. So again, that's going to be an open dot. Use our slope of negative 1 here to go down 1 over 1 and complete our graph. There's our second piece.